voy a cambiar de ingreso. Este es el plan. This is the line of the talk. I'm going to talk about also cross collisions, and then about neutrino masses. So as a recap, this is I've shown this plot many times. You have the wedges of the correlation function from 9 alpha and 9 alpha, and we are computing this in the project, in the project with using exactly this. As a function of r instead of r verb and r total, and you can see here we're creating these different models of Gale, and each of those models has a different assumption. Here, first blue line is line of cosmetics. The second one includes HTTs, UV, UV, and so I'm going to go through these things. So this is the list actually of things that we tested to make sure that this makes sense. So there's a lot of systematics, and for instance, we try to analyze astrophysical systematics that arise from, for instance, system, UV background, GV, and other that come from the instruments. So how the flux is calibrated, the sky is well subtracted from the spectrum, if there's any control between fibers, etc. And all this was tested with the data and model catalogs. I'm going to mention those two here, those both, that I think are the most interesting. First one is the metals. So there's other species as did you find a point? Okay. There's other species than diamond alpha in the Quasar spectrum. You saw that the Quasar spectrum has a Lambda peak, but it also has a silicon 4 peak and a carbon 4 peak. So as you have the forest here corresponding to hydrogen, you also have absorption by carbon 4. So you have a carbon 4 forest, and you also have a silicon 4 forest. They are much smaller because the body is much smaller than this. To scale, but this is much smaller than but it's there. So you can actually measure the correlation. You can do the same analysis you do in the line of forest. You can do on these two regions here. And so here I'm showing the plot from this paper where they do the continuum fitting on those regions of the spectrum, and they compute the correlation function, and they do see some signal that is corresponding to lambda CDM cosmological model, and from that they can derive a bias for this assumption, this carbon 4 absorption, and the bias here is much smaller. It's 0.01, while the line of forest is 0.1. Okay, so it's like 10 times smaller bias, and it's a contamination for the line of forest as well, because as you see, this forest can go all the way, and they overlap in the forest region, not the forests. So you have this sort of contamination. It's a small contamination, and we wanted to test if this contamination changes behavior or changes the correlation function. So what do you do how do you separate the absorption from lemon alpha and the absorption from carbon 4 or silicon 4? We're lucky to have actually low redshift quasars. We have low redshift quasars where lemon alpha is here, and then you have the spores that appear at the same redshift but without the lemon alpha first, right? So you can compute at the same redshift using those low redshift quasars. You can compute the correlation function from those regions and compare to the correlation function from here, right? Because it's the same redshift. So this is the results, and for instance, I'm showing the most important. Oh, thank you so much. I'm showing the radial wedge of the correlation function, and this is the carbon 4 correlation function at the same redshift, and this is the lemon alpha one. So you see, this is consistent with 0 at this statistical level, these error bars. You see nothing, it's consistent with 0, so we are not much worried about this. But that's not all. with metals. Not only you have carbon 4 and silicon 4 at a very different shift, but you also have those lines such as silicon and silicon 2, silicon 3, and this is the wavelength of rest frame of those transitions. And Lyman alpha is the wavelength is 1216, and you can see the wavelength for those transitions is very close to Lyman alpha, very, very close. So these lines are in the forests, and you actually get confusion from those lines. And the equivalent separation, if you look at radial separations between these lines, those separations correspond to 7, 21, 31, 38 megaparsecs of range in the radial direction. And interestingly, this line distance is exactly over the BAO peak, where you expect the BAO peak to be at 100 megaparsecs over range. So we did some tests, so you can see those lines very easily if you do the one-dimensional forest. Okay, and this is what you have. You actually see those spikes as a function of lambda or difference between the lambdas. You see the correlation function and those spikes caused by those fake correlations introduced by this contamination. And in particular, those that translate to the 3D correlation function, they appear such as these peaks here, this first peak. Remember, on the most radial edge of the correlation function, you have this second peak, but that is not a BAO peak, it's a metal peak. And this is the correspondence between the two. This first huge peak is actually hidden here. You don't see it much because of the R2 scaling of correlation. And this one, oops, sorry. This one, these two peaks melt into this one. And the third one, this one is the one that's over the BAO peak. So on the model, we have to include those contaminations. So what we do is that we have a model for the Lyman alpha correlation function, and we do copies of this at different separations with different bias parameters. So one bias parameter for each transition. So this is what creates this peak here. It's the correlation function at 0 of the Lyman alpha metal correlation. So there's two parameters for each metal transition, and then we do a fit of those parameters, and we marginalize all those two parameters. So what's the impact on BAO? Does it change results? No, it doesn't change much the results. Tests on MOX suggest that you should include those metals, otherwise you get a bias on BAO. So we get a much more robust, but also we have an increase of the error bars. Since we have two more parameters, the error bars increase in the final BAO constraints.
Wait.
Yes.
Okay. Why does it 1207 like
Which one?
1207.
12?
Yeah, silicon.
This?
1207. The one that is at 20.
This one?
Margin, yeah.
No, it's not a tip. It's actually the correlation function goes down like this very quickly, and you have a small bump like this.
Okay.
Yeah. It's hard to see on this space, but it's actually big. So yeah, that gives you the first blue line. That's why you have this piece. The second line in the model is called, we try to model the effect of damped Lyman alpha systems. So what are these? So if you look at some spectra, actually 80% of the spectrum of forests, they show this huge absorption. That's a trough, and with those wings inside. This is just a very, very high density region in the forest caused by, let's say, a galaxy, a small galaxy forming. You have a high density region with very high fraction, with that neutral hydrogen fraction is actually higher than the rest of the universe. So what happens there, when this density is high, the UV photons that are high in this region cannot get inside the region of here. So what happens is that the fraction here does not come to the average fraction of the universe. So it has much more dense blob here of gas, neutron hydrogen. So then when the light of the quasar comes through you see enhanced absorption. And the bias of those things changes, right? Because you assume that the neutron hydrogen fraction is the same all over the universe. But here, this breaks down, this assumption breaks down. And that's why you see such a large absorption.
The inhomogeneity of the UV background can also have an impact?
Yes. Yes, I'm going to show one plot. Exactly. So yeah, we'll talk about that later about very large UV fluctuations. But this is a very localized UV fluctuations if you want. Okay. So the opposite of that, we can write it as a function of something they call the column density. Is just something that's related to the number of protons per centimeter square in that location. Carbon that we use in the field. But most of the forest has column density 10 to the 13, 10 to the 16 atoms per centimeter square. But those systems here, they are much large densities. So in the data, it's quite easy to find those DLAs if you just run an algorithm that scans through the spectra and tries to find those tips, the struts in the spectrum. You can find those DLAs. But you have also those systems that are quite high density, and they work like this, exactly the same, but they are hard to find because of the noise. So they are there, and they contain your signal. So there was several papers talking about this. One of them is Rogers et al. Slides later if you want to look more. They look at simulations, hydro simulations. And they look at what's the difference between power spectrum, where you have delays and laminated systems, or those, and one you don't have. And you see this is the green line is the radial correlations, and then this one is the transverse correlations. And you see, quite important changes. Even this up to 15% increase on large scales. Okay, and it's a function of scale, and it goes like this, down. If you can do like the data, you can find the big DLAs and you cut them. This is what happens. You still have the residual small DLAs that you cannot see, and you see this contribution. It's much smaller. You have up to 15% increase in the power, and it's a function of mu again. So it's very important to take this into account when you model the correlation function. So this is how we model it in the fit. It's just introducing, this is the bias. We have a new effective bias and a new effective beta, where gamma alpha 1 here, and you have this contribution coming from this DLA. This is high column density. So you have this contribution, and this F is just an exponential. And
it doesn't look like it also depends on the redshift.
It also depends on redshift, exactly. So here we don't include this dependency because we do just one measurement. The BAO measurement is the correlation function in one effective redshift. But if you do the analysis at two different bins, then you need to change, for instance, this L scale. Yeah. That's a good point. I didn't mention, but there's two, one low redshift and one high redshift. And it seems that the impact at higher redshift is smaller. So okay, so again, this plot I'm showing. So now lambda alpha plus pentals plus HCDs. You have these two first, and you understand that it doesn't actually change much the fit. You can see here. A slight increase in the power in this region here, and a slightly increase in power here when you include this contribution from the LAs. So, as Josue just asked, you also did something called UV fluctuations. As I said, you assume that the universe is a constant neutral fraction of hydrogen. but maybe we know it's not, right? It's an approximation. So quasars, so the neutral hydrogen fraction is not the same, it carries across the sky. And you need to model that, and there's people that work on this. This is one of the papers that has a modeling of this effect, and this is how it changes the correlation function. The dotted line here is when you don't have fluctuations, so you have this. And when you do have those fluctuations with different parameters or different assumptions, you have this kind of distortion. We include this on the fit as well with the HCVs and metals, but it doesn't improve the chi-square much. So, and that was the third line on that plot. When you add UV, so you don't see much change with respect to the previous fit, right? Great. So that was, yeah.
It seems that it's not changing nothing on sky square just because it's like a constant, so it's mitigating the bias.
Yeah. The feature is not as different than just the bias. So you have homogeneity first of all with the bias of lambda alpha, and then you don't improve much the fit. Okay. Any questions on the lambda alpha BAO? Now I'm going to talk about cross correlations. So you don't have only forest for each quasar. You don't have just the forest that's a tracer. As I said in my first lecture, there's also trace. It's a galaxy. There are also galaxies. So they trace the very high density peaks of the density field. So what you can actually do is start with correlations between the quasars themselves and the forest. And this is what we call the quasar-forest cross correlation. So this was first measured by Andreu Rivera in this paper, and then where they actually measured BAO for the first time, and all the last measurements is described here, and this is the plot of the last up-to-date measurement of the cross correlation between quasars and lambda alpha, and you can actually see the BAO peak here appearing, and you can see that this is now negative. You can see that the correlation function is negative. And this is because the bias of the forest is negative. Remember, the lambda alpha autocorrelation is bias squared, so it goes positive. But here you have a quasar, which is a positive bias tracer times a negative bias tracer, so you have this negative correlation function. And you can see the peak very clearly here, at least here and here. These are the constraints on BAO. This is alpha perpendicular, transverse BAO and radial BAO. And from the autocorrelation here, from the last paper, there are 14. So you hear the red contours is 1 and 2 sigma contours of just the autocorrelation. And when you combine the constraints with the cross, assuming they're independent, you have the black ones, smaller contours. And this is Planck, the prediction from Planck. This was a big deal in before these papers because the tension was about 2.5 sigma between the black one and the dots, but now it's reduced to 1.7 sigma. And so here to compare what's the constraints from lambda alpha quasar cross correlation alone, this is how it compares. So the black lines are still the same, and you can see the difference between the autocorrelation here and the cross correlation. Okay. So the tension reduces from 2.3 sigma to 1.7 sigma. So, okay. So as I said, you have those blobs, right? Where is it? Here. So you have those blobs, those DLAs. As I said, they are also proto-galaxies or galaxies you don't see. So you can also use them as tracers and compute what is the cross correlation between those DLAs and the forest. And you have something like this. About 20% of those come to DLA, so there's quite a lot of statistics. Fortunately, you don't see BAO there. But what you can do is to compute a bias for those systems. Those systems are quite mysterious yet, so we don't know much about the physics of them. So you can derive a bias parameter, and it's about 2, which is very similar to the bias of galaxies, right? So you can derive a host halo mass for those systems as well of this measurement. Okay, so that was it for BAO. Now I'm gonna talk about something very different, a different type of analysis, and that actually can constrain neutrino masses. And it's very promising with the forests. So this is a plot showing what is the impact on the matter power spectrum, on the linear matter power spectrum, caused by massive neutrinos. So here I'm showing again the ratio of the power spectrum with a massive neutrino with respect to a massless power spectrum as a function of k. And what you see here is that the power spectrum gets damped at small scales, which are small scales, and those small scales are probed by the lamina of the forest. Those large scales are probed by the CMB, but the small scales are accessible by the lamina of the forest. And then depending on the mass, the red one is 0.5 electron volt, and these blue lines are 1 electron volt. They're quite big masses. And as a function of redshift, again, that's really nice. So you can see here that if you combine lamina alpha and the CMB, you can actually measure the mass of the neutrinos. So this was done. For the first time, was done in 20. Sorry? Yeah.
Those curves are linear theory, right?
Yes. So the challenge here is to measure the linear power spectrum on those scales. And there are very small scales. And what happens in small scales when you look at clustering is that you have no linear effects coming into your physics. And for particularly the lamina alpha, you need to understand the gas, right? The gas motions and gas physics on those scales. So I'm going to show you how this is done in some slides. So this is the measurement. So you pick one forest, you compute the Fourier transform of that forest, and you go to Fourier space, and then you compute the power spectrum from those forests. So basically, you compute the variance of, and that's what we call the 1D power spectrum. And this is shown here. This is the power spectrum times K, and this is K in some weird units, kilometers per second inverse. And the reason for that is that we're using velocity space in the spectra. They have constant size in velocity space. That's why you have this weird K. And I show you here how to convert between K and megaparsecs. So to have an idea, it's a bit hidden here, but pixel size is about 69 kilometers per second. That corresponds to 0.3 megaparsecs over each. And this is equivalent to 0.09. 0.09, it's way up here, and the analysis is going to 0.02. And this is about 1 megaparsec or a few megaparsecs. So you can see here the error bars are actually there for all the points. They're super small, and as a function of redshift. So you can see the evolution of the power spectrum, the amplitude of the power spectrum increasing as a function of redshift, and you can measure it super accurately. And this is the last measurement from very December, I think, from combination of BOS and EBOS using 43,000 forests. So how do you analyze that? You cannot just fit a simple model, an analytical model, or an approximate model. You really want to measure it correctly to get the mass of the neutrinos. So you need a model that actually takes into account all the physics, all the nonlinear physics of your forests. So what you do to analyze them is to run hydro simulations. So they do hydro sims using algebra, for instance, and then they vary the cosmological parameters and they vary the physics, the parameters that give you the physics of the gas. These simulations are described here in these two papers, and they have different sizes of boxes and resolutions. This is the physics that comes into those simulations. You have adiabatic cooling, UV ionization, recombination, feedback, AGN, etc. And also neutrinos, the most important part in neutrinos. These are the cosmological parameters and that give you the grid. So they vary sigma 8, they vary the spectral index, H naught, omega n, and some temperature parameters of the gas. And also, of course, they do this for different masses on the neutrinos, 0.1, 0.2, 0.3. This is how they look like. This is a picture of a snapshot of this is the gas, this is dark matter. I'm gonna turn off the lights a bit so you can see better. And so this is the dark matter, and this is neutrinos for a mass of 0.1 eV. And this is the corresponding one for a more massive neutrino. So I don't know if you can see the differences here between these two, from top and bottom. There are very, very small differences. And I can point out to one of them is that, as I said, more massive neutrinos, they damp the small scales, right? This corresponds to some sort of smoothing. So, so you can see that the high density peaks of dark matter are not as high in a more massive neutrino because they damp those small scales.
Yeah. It's the other way around.
Huh?
It's the other way around.
Why?
So less massive neutrinos and down smaller scales.
No, the damping depends on the mass. The more massive, more is damping. The damping is larger, so the power spectrum is smaller, right? Sure. So this is 1 in eV, this is 0.5. So the smoothing here is larger. Come on, you have less high densities here than here. This doesn't show as red as this one. You have a question?
It's for the hierarchical model. So it's with one massive, one neutrino with much more massive than two others.
So that's a good point. You cannot simulating neutrinos is a very tricky thing. So what they do is just simulate one species here. Yeah. So you cannot really do the difference.
Mass to one.
Yeah.
One neutrino. So if not, it's equivalent to a half-ordered mass. Typically,
Yes. Spectrum from those simulations. For each of those simulations, you do some sort of emulator, an interpolation between those simulations, the power spectrum derived from these, and you compare to your data. And that gives you this, you can do, so you do a grid on omega n and on some of the mass of the neutrinos, and these are the constraints. So on blue, this is the constraints from the CMB, from Planck, shown here, 1 into sigma, and this is coming from the Lyman alpha forest power spectrum. And this is the mass of the neutrinos, and if you combine the two, you get actually this green contour here. And you can also do the same, play the same contours game with the sigma 8 parameter. And what you derive here is that the sum of the mass of neutrinos is about 0.15 electron volt. That corresponds to here. At 2 sigma, at 95% confidence level when you combine the two. So we're actually reaching the limit where we know that they do have mass from ground experiments. And the mass, the minimal mass that the neutrinos can have, the sum, is 0.06 electron volt. So you can see here, this is just about 2.5 times the limit of the masses. And this is just false. So you can think of, maybe the next generation of surveys will be able to reduce this a bit more. And then with that, for the first time, the constraint on the mass of neutrinos from the combination of Lyman forest and the CMB. And this is very tight. So the future of the Lyman forest cosmology. So as I said, if you have more data, you can do a lot of stuff. And there is more data incoming. You heard about DESI that's coming up starting this year. And other spectroscopic surveys that are coming up too. Euclid, WFIRST, there's satellites, And there's all our this DFS is a 8-meter telescope. This is a 4-meter telescope again, and they all measure spectrum. I'm going to talk mostly about DESI, which I'm more involved. So DESI is going to be much better than BOSS. And here are some numbers that compare the two. This is BOSS, and this is DESI. EBOSS has a 2.5 meter, DESI will have a 4-meter telescope. The sky coverage will be 14,000 square degrees. This is 1/4 of the sky. Instead of 1,000 fibers, there are 5,000 fibers per observation. Instead of being plugged by humans, they'll be plugged by robots like this. So this is showing one of the robots that's going to the focal plane. So there are 5,000 of those together in the focal plane like this big. And this is how you see it from above the focal plane, the little heads, and how they cannot be on the same position. You cannot put two fibers at the same location, so they actually collide. So that this creates some patterns that you can see in the clustering. You can contaminate the clustering as you saw yesterday. So this is much better than this plugging by hand. This is the past. And this is it's actually showing how it moves. So all those robots for each position in the sky, you just tell the computer where I want to look, and they move around the axis just a tiny bit. So yeah, I think this is a huge improvement with respect to the plates one, because once you have months to prepare those plates before the observation. You need to drill those. You need to. It was University of Chicago, of Washington, that were drilling those plates, and they were sent by truck to the mountain, and then you had to plug those fibers by hand. So the planning was much harder. You had to plan in advance, and you could not change. Here, you actually the day before, basically you can say, I don't want to observe these. I can observe this field now, and the fibers move and point to whatever you want. This is again a picture of a petal. Is 1/10 of the focal plane. You're going to be 10 of these guys. So you can see that each of those robots already plugged, and the fibers coming out of these. You can imagine the amount of work to prepare all this. So what they're going to observe, very similar to BOSS or EBOSS, they're going to observe mostly ELGs and also LRGs and quasars. And this is the redshift distribution of those tracers from 0 to 4. And you have a very bright galaxy survey. It's going to be complete up to redshifts of 0.4 or something like this. And then you have ELGs that go from 0.5 up to 1.6. And some LRGs that have a very similar distribution than EBOSS. And also lots of tracer and Latin alpha quasars. The density is very low, but this is not important because, as you know, one quasar gives you a lot of deltas. Right? So this is the constraint on BAO that you expect from DESI compared to other surveys. So the blue line is showing from BOSS, the results from BOSS. The green one is EBOSS. That's the present, and these measurements are about 1 and 2% level from BAO. For DESI, what you expect, or HETEX or these others, is to have below 1% measurement of the distance scale, of the BAO scale. And it's crazy the accuracy you can get as a function of redshift. The black line and the dotted black line are for two different areas. Let's say something happened, you don't observe 14,000 square degrees in the sky, you observe just 9,000 square degrees in the sky, and you have a slightly decreasing of the errors, but still very impressive. If you plot the distance scale as a function instead of the BAO scale, you plot h of z. Remember this plot? I showed this one where you put the BOSS constraints here. This is Lyman alpha, this is galaxy ones. DESI will do this. hopefully. So look at this, very tiny error bars, it's crazy. So if you have a dark energy model that doesn't fit this data, yeah, you can exclude it. So hopefully we'll be able to constrain more or to reject some dark energy models with these, and maybe see some departures from lambda CDM, who knows? So I'll so you can see how the error bars. This is from VAO, and this is a very interesting plot showing some physics. This is geometry, right? As you go to zero redshift, you don't have volumes. The volume decreases. You cannot see as much sky. So the error bars increases just because of sample variance. You don't have the volume. So for low redshift, VAO is not good. It's not very good. You need to do something else, like supernovae. But for higher redshifts, so you have the galaxy survey here and the quasars up to redshift 2, and you see the error bars increasing, and that's because the density of tracers is going down. And then after redshift of 2, the error bars go down again. And I don't know if people that were working in projects know why. What's happening at redshift of 2? Can anyone tell? What is special about redshift of 2?